Hello everyone, welcome to the last lecture in this class, lecture 19, which I've entitled Distributed Computing. We also might think of this topic as being big data or big data analysis. Last time we talked about different computing platforms, the difference between virtual machines, containers, and serverless functions as different levels, different ways to abstract the computing platform. With virtual machines, we talked about the general idea of virtualization, which allows us to run multiple operating systems at the same time in one physical server, to kind of split up a server into little pieces. That's important, especially in cloud computing, where you can rent just a small fraction of a machine, which makes it a lot more economical. This is also important because it allows us to distribute an application and all of its dependencies, like libraries and the environment that's needed for an application, as a virtual machine disk image, which is a file that represents the contents of the virtual hard disk in that virtual machine. Containers are an evolution of that concept, where we still are creating a consistent environment for an application, but it's done in a much more lightweight way than a virtual machine. We can distribute an image, but we have a different way of doing that. We have a layered file system for sharing images on a single machine in an efficient way. We also have a way to distribute a container as a Docker file, which is kind of like a blueprint or a recipe for building that image, which is also much more efficient. Finally, we talked about serverless functions, which are a way to put code in the cloud that's ready to run, but not actually associated with any particular machine. Those serverless functions are deployed and run on demand as needed. So at any given time, you might be using 0 machines to run your code, or thousands. So you get really dynamic, fine-grained scalability, much quicker response time to scale than containers or virtual machines. So today, again, we're talking about these like big data analysis problems. And so far in this class, we've talked about what I would actually at this point call relatively easy scaling problems. So it's relatively easy to handle lots of independent requests from millions of customers because you can use a divide and conquer approach. So scaling up your system horizontally it's not really easy. Obviously, we had to talk a lot about a lot of concepts to make that work, including ways to make databases scalable. But still, we'll find that today we're going to talk about problems that are more difficult in the sense that we can't just add more machines that are doing the same kind of work to do a lot of stuff in parallel, but instead what we're trying to do now is to do essentially one big calculation with all the data from millions of customers. So to scale up the size of the work that we're doing, the individual units of work, rather than the number of units of work that we're doing. Okay, so for example, a case when we would want to do one of these big data analyses is like if we have all the data from Amazon.com's order history and we want to build a recommendation system. So in other words, a model for what a user might want to what they might want to purchase next given their history of purchases. That requires a lot of data, and all that data all that data is relevant to modeling the purchases for any particular user because of the interrelationships between products. So to do this, solve that kind of a problem well, you need to actually make use of a lot of computers at once to solve that problem, to do that calculation. You need to share a lot of data. And today we're going to be talking about ways to do that. There are specific tools that make that work easier. We're going to be talking about MapReduce and Spark in particular today. So we're scaling up to solving huge problems, like one single huge problem. We're not worrying if the calculation might take several hours to compute. That's okay to finish. But again, we're trying to scale up to handle lots of data. So I would call the term big data is used a lot these days in a very loose way, but generally I would consider a true big data problem to be one that cannot be solved on a single computer. Okay, so for example, if you only have one computer, there's a limit to how much data it can read, the rate at which it can read. You can use the PCI Express bus bandwidth as a upper bound. So if you have, let's say, 10 petabytes of data, then it would take 35 hours at the very least to even just read all that data in one computer. And this calculation is really unrealistic because it's assuming that you're making perfect use of the PCI Express bandwidth, and you're doing nothing else except reading data. Even then, it still would take 35 hours to read all that data. If you want to get that done faster than 35 hours, then you need to somehow split up the work across multiple machines and work on it in parallel. So we want to do analysis in parallel. And so we split the problem into pieces somehow. I mean, how exactly you do that will depend on the problem. You have a bunch of machines that will split that work. They'll work on subproblems that contribute to the final solution. And we have to somehow redistribute intermediate results in working toward the final result. And this is researchers have been and practitioners have been working on different ways of doing parallel data analysis for many decades. This is an ongoing area of research and development. So it's rapidly evolving, but some of the ideas have been around for a long time, but then there also are a lot of advances being made. But the general idea is, with what I would call distributed computing, is that you have a lot of computers, a cluster of computers. They each have their own capacity to do some computing, right? They each have their own CPU hardware, their own memory. They also have some storage, and you split up the data among lots of computers, right? You have so much data that it's not even possible for one computer to store all the data, or it's also not a good idea for one computer to store all the data, because then it would take a long time for that computer to process all of it, right? Because the CPU bandwidth, I/O bandwidth is limited. So you split up the data. So see how I have data split across all these machines. We have some kind of communication network connecting them. And then maybe we have a control node that is also connected to the network, where you start the program. And then you in order to do this well, you need some kind of special way to define these analyses. So in this class, in this lecture, I'm going to be talking about two different platforms. Hadoop and Spark are essentially computing platforms or frameworks for building these kind of distributed computing algorithms or programs in a way that's like easy, because the framework gives you a lot of the common tools that you'll need. But of course, you can do this in any language that has the capacity to communicate over a network. Okay, you just need to write your program in such a way that it knows who to communicate with, what data to exchange, and so forth. Okay, so just to give you an example of what I mean by distributed analysis, let's consider a simple problem of finding the largest sales order in a big data set. Okay, so we have a lot of orders. They're actually distributed across a bunch of machines. So I'm showing that I'm splitting up the orders by month, January, February, March, and so on, across these different machines. I have a control node up here, a primary node, and it has a program. And what it does at first is distributes that program to all the computers, to all the nodes in the cluster that are going to be involved in the calculation. This is just an example at a high level. Each one computes the maximum of its own data. You see the results here shown in pink. All right, they all have different orders, so they're all going to get a different answer. And as you can probably guess, because the maximum is kind of like I forget what the right term is for it, but if you have you can apply it in like two steps, right? The maximum of, if you want to get the maximum of a set, you can compute the maxima of the subsets within it, and then take the maximum of those results to get the final answer. And that's what we're doing here. Each of these nodes is going to do its calculation in parallel at the same time, and then send its answer to a single place. In this case, the central control node. And then among these results, there are only 6 of them now, this control node can quickly figure out the maximum among those. Okay, so most of the work happens in parallel, so it's pretty efficient in that sense. We're making good use of all these different computers if we've divided the work equally, and if we have a problem like this that's like trivially parallelizable, which this definitely was an example of something that's really easy to parallelize. Final step, we just take the maximum of those maximums, and that final step is happening on just one machine. So we're not taking advantage of the other machines at that final step, but it's a really small step. It just involves taking the maximum of among a handful of different numbers, whereas there could have been millions or tens of millions, billions of different orders in these individual machines. So that was where the bulk of the work probably was. Okay, so this maximum aggregator is trivially parallelizable. Most of the work can be done with little coordination, no coordination. At the end, there's just a little bit of coordination through that communication that's required. I want you to stop and to pause and think about what other calculations are like this that can be easily parallelized. What do you think? Well, there are other aggregators that are similar. Like, of course, I showed maximum. Minimum is another example. Summation is another one. All right, if the sum of a set of numbers can be computed individually on the subsets, and then the sum of those can be made. Searching is another one, right? If you want to search for a particular thing, you can break it up into pieces and search in the individual parts, and then aggregate the results. Like, show me every time a certain word appeared in this whole set of documents. You do that work individually, and then join together the results. Mean is another example. It's actually to calculate the mean of the mean average of a lot of numbers, you need to compute the sum and the count in parallel, and then that can be joined together to calculate the final mean. Now, I'm going to give you an example of a slightly more complex problem. Median, right? If you want to compute the median, which is to say the value that's right in the middle of all the values, if you were to order them, right? How would you do that in a distributed manner? Now, I want you to actually stop and think about this. It's a pretty fun challenge. To do this, if you don't know where to start, I would suggest you look up the quick select algorithm, which can be used to find the median on a on a single computer. And that same approach can be applied in parallel. Well, if you've stopped and thought about that, hopefully you have an idea of how to do that. So just like with quick select, what you do is you choose a pivot value. The pivot value is it would be shared by all the nodes, right? So you have the leader choose a pivot. The pivot is the value that's going to be like, it's a candidate for the median. It's like a guess as to what the median is. You can just pick the first value and try that, and then you give it to all the nodes, and each node for its data set rearranges the data into two sets, the L and R, those that are below the pivot and those that are above the pivot. And the nodes count the size of those two sets and send the size of basically they all tell the leader how many nodes were smaller than that pivot value. The leader can sum those all up and that will tell it how many nodes across the whole system, how many data entries across the whole set were less than the pivot. Right? If the answer was exactly 50%, then you're done. That's probably not going to be the case. But then you can just decide if you based on that, you'll know whether you need to choose a larger or smaller pivot in the next iteration. You do that kind of like binary search in that way, but you only recur on one half, not in both halves. So you end up with a linear time algorithm. So for example, if the number of items that were less than the pivot is less than half of the total set, then that means the pivot was too small, so you need to choose a larger value, and the opposite if it was greater than half, until eventually you'll find the correct value. If you know roughly what the minimum and maximum values are in the set, then you'll eventually you'll converge in a logarithmic number of steps. Although I guess if you're using numbers in a computer, then there is always a limit to the size of the numbers. So in any case, you'll converge in a logarithmic number of steps. Cool. Okay, so again, the basic idea here is that with all distributed computing is that your input data is split among the nodes ahead of time, or you do it at the start. Your code is distributed to all the nodes. You have rounds of communication. Generally, you can't just work totally independently. You have to exchange data in some ways. In the simple examples I gave here, the first one with the maximum, there's just one communication at the end. In the case of the median, there were many rounds of communication. In every round, the nodes were telling the leader, how many items were in the set that were less than the pivot. But eventually, in the end, you come to you finish, so you have a finite number of rounds. Now, distributed algorithm. Basically, if you're writing in a programming language that allows you to use a network, then you can implement distributed computing. But rather than have to build it from scratch to figure out the right strategies from scratch, we have distributed computing frameworks that let us build these kinds of analyses using like the patterns provided by the framework, which make things a lot easier. MapReduce and Spark are the two we're going to be talking about today. And an interesting analogy I want to draw here between these distributed computing frameworks and something we've seen before is with databases. So relational databases are basically any kind of database. A database is a off-the-shelf software for dealing with the problems of storage, persistent storage, and searching, right? You could always build your own system for doing storage and indexing and all that stuff, as long as you have a programming language that lets you access files and a network and stuff like that. But you normally wouldn't do that because generally a lot of people are faced with the same kinds of storage and indexing problems. Therefore, these general purpose reusable database softwares are quite useful. The same thing applies to distributed computing, right? When you're doing distributed computation, the same kinds of things are needed. Like you need to do communications, you need to scatter data, you need to gather data, you need to sort data, things like that. Frameworks like Hadoop and Spark provide you with like the basic building blocks. MPI is another example. Building blocks that are quite commonly needed in distributed computing, and therefore let you get the job done much easier than if you were doing things totally from scratch, just like databases do with storage. Cool. Okay, so we're going to start talking about Hadoop. Hadoop has two main components. So there's actually a file system that comes with it called the Hadoop Distributed File System, HDFS. The reason why Hadoop, we're talking about a computing platform, but we're also talking about a file system, is because to make a parallel analysis on a big data set work well, you want to actually run the calculations as close to the data as possible. You want to avoid transferring data as much as possible. So the Hadoop distributed file system, it's just like any distributed file system. It stores files on many machines and has some way for you to find, discover which machine you need to go to find a particular file or a particular part of a file. The Hadoop computing platform works with that in the sense that it defines analyses over these files, these large sets of files, and it implements them in a way that runs the code on the same node where the input file is stored, or it tries to, right? So it optimizes the efficiency of the system by being aware of where the data is stored and having the ability to run code in that storage location, rather than having like a distributed file system over here on one side that has a bunch of nodes storing data, and then in another place you have the cluster of machines that are doing the calculations. Like if you have the storage here in one place and the compute power in a different place, you have to transfer everything over, right? If you could somehow, what Hadoop does is combine the two, so you can run your calculations, like you read off the disk into the CPU directly without transferring over the network as much as possible. That's a good approach. And keep in mind also, this is the same kind of thing that database software does. So if you're using a SQL relational database, you can write SQL queries that do analyses. And actually, that's like kind of a special case of this although it typically operate on just one machine, but you define analysis in a particular language, and it ends up with SQL, and it ends up running on a relational database, like on the same machine where the storage is, where the data is stored. And so it doesn't have to, so it does that efficiency because it's reading from disk directly to the CPU and doing the analysis and giving you the result, rather than copying all that data to another machine and so forth. Okay. So in addition to that Hadoop distributed file system, the important computational piece of Hadoop is MapReduce. So MapReduce is a programming model for defining parallel analysis steps. So it actually is pretty unusual and restrictive in the sense that you have to define your programs in a very specific way using maps and reduces. Because of that amount of it restricts you a lot in how you define your programs, but because of that, it allows your program to run on a variety of different programs written in that language. No matter what program it is, it can be mapped to a runtime system that handles running it in an efficient way. So this is MapReduce Hadoop is an open source implementation of MapReduce. MapReduce is an idea introduced by Google publicly in 2004, an article that they published on MapReduce, very famously. The code you write usually is written in Java, but other languages are possible now. Originally it was Java, but Hadoop has become a very popular tool, so lots of languages can write these MapReduce operations. So I'm going to talk a little bit about this in a few slides, give some examples, and then we'll move on to Spark as like a evolution of this. But anyway, with MapReduce, what you have is, like I said, it's a framework for parallel processing. the key thing about it is that it imposes a certain pattern. And at first, this will feel really restrictive and frustrating, because usually when you're programming, writing software, you have a blank canvas and you can do whatever you want, basically, right? Like you can, that's one of the cool things about writing software, right? MapReduce is different. You have to do everything with maps and reduces. Now, the code of your map and the code of your reduce can be whatever, but there are only two functions that you define, and the form of the input and the output is predefined by the framework. So you have to work with these two functions that have a particular signature, and then there's a scheduler and data like distribution pipeline built around that you have to work with. Okay, so your input comes, it's split up to map tasks. The map tasks do something, like whatever happens in this map task is going to depend on what you're trying to implement, right? So you write the code for the mapper that produces some intermediary results. So there's this middle part is where intermediary data is shared, and it'll be transferred to other machines that are involved in the calculation. They're kind of gathered to the reducers, and I'll talk about how that happens. And those do the final step, so it's a two-step process, and those produce the output, right? So you have to make your algorithm work in two steps. Although, of course, you can break it into, you can chain these together to have MapReduce, MapReduce, MapReduce. But in general, you're breaking everything into map and then reduce, and the framework is doing a specific thing in between that I'll talk about. Okay, so with map, the map function, I have these diagrams to kind of like help you understand how they work. So mappers take in a key, which is your data inputs. Like typically they're like lines from files that are stored in a Hadoop distributed file system, and so the key is usually the file name, and the value is typically the line of text. So you have a bunch of files that are stored in a folder, basically, in the distributed file system as inputs. You want to process them, so you write a mapper that operates on a single line. For every line of input, you write code that produces a list of output keys and intermediary values, pairs of those things. How you would use them, what the meaning of those would depend on the algorithm you're implementing. So you're producing a set of intermediary pairs, and the reducer works on those intermediary pairs, the reducers. So your reducer takes as input an output key. Remember, that was the same key that was produced in the last step. A list of all the intermediate values that were produced across all the mappers for that key. So there's kind of a gathering in the reducer of all the values for that same key, and it produces a list of output values. So what the purpose of the reducer is kind of to merge intermediate results that were produced in the previous stage from the multiple different machines that were operating on different lines of the input. Okay. So as an example here, the example I'm going to give, this very simple one, is counting words. So we have a bunch of text files in a Hadoop distributed file system folder, just a huge amount of documents. We need to define a mapper and reducer that together will have an output that is actually, this is counting the number of occurrences of each word. This is not just counting words in total. It's more complex than that. It's counting the occurrence of each particular word in the dictionary, in a set. So basically, we want to what we're doing here is counting the frequency of words. Sorry, that should have been counting frequency of words, particular words, right? Okay. So the mapper is the first step, right? The input is going to be, the input key is going to be the document name, like the file name. The input value is going to be the document contents. It could just be one line of the contents, or the whole document. Doesn't really matter in this case for this particular problem. And in the runtime system, you might be able to control exactly how the documents are split up into inputs. But let's just assume that it's the whole document, or a line of document, doesn't matter. So now in using this framework, we're able to define this mapper. So what we do, if we're clever and we have a good handle of how to use map and reduce, we might come up with this solution, which is to, in the map stage, go through all the words in this input. So we break the input value into words by like splitting on the spaces. And what we return a list of, for each word, we return that word and the number 1. Like we return a list with one element. That's what this is here. A list with one element where that element is a tuple of the word that we saw and the number 1. Okay, so basically what we're doing is every time we get a document, we split up the words, and for every word we output the word and the number 1. So the word is the intermediate key, the intermediate value is the number of 1. In the reduce step, which is the reason why we did that is because in the reduce step, the intermediate key, which is the first value that's output in this tuple in the map step, that's used to gather the intermediate results, so they can be processed in one call. So this reducer will be called once for each output key, in other words, for each word across the entire system, across all those documents. So we define this where the output key, the meaning of the output key again has to match what we were producing in the previous stage, so it's a word, and then we're going to get a list of intermediate values that were produced. We were getting it as an iterator in this case, in whatever language this is, kind of pseudo Java and in the implementation of the reduce, all we do is basically count them up. So we start off with 0, and then for every one of these intermediate values, we add the value we got to the what we have so far, and we return the value that we got. So this will count basically I'll take all the ones and add them up for each word. Okay. So to visualize that, we can use this picture. So here's an example of an input. It's broken up into lines, or those lines are each go to the mapper. So we have many instances of the mapper. They're operating on one input each. And remember the way we implemented it was to break it into words and output the word and the number 1. So you see that these green boxes show the mapping outputs. And then the tricky part of this, or the interesting part, and we didn't even write code for this. What's interesting about this is that with MapReduce, there's some steps here that are done automatically by the Hadoop runtime system. And these are very important steps that we can take advantage of. So the first one, which is not super interesting in this case, is the splitting. So we automatically split the input documents into individual lines. Okay, and then we process those individually. But the more interesting one is here, what's called shuffling. So we take all these outputs that were produced, all these green outputs that were produced by the different mappers, and we look at the keys, the intermediate keys. And we kind of sort them and merge the values when we have the same thing. So Hadoop appears many times, 3 times. In this, we're going to do a big distributed sort of all those output values, and all the Hadoops are going to go in the same place. So we have Hadoop 1, Hadoop 1, Hadoop 1. So these together are going to go to one reducer. The reducer is going to get the key, as well as it'll get this list of 3 ones. This little arrow here between green and blue shows what happens after the reducer runs. So the reducer output produces 3 because of the code we wrote is what made the 3. And that happens for all the other words. It also sorts them so that they're in order. And so the output ends up being, I guess there's also implicitly the runtime system will join all the different outputs from the different reducers and produce a single output, although it might be distributed across many files for efficiency, because you want to use that Hadoop distributed file system to store things rather than having one big file. So that's how we got a list of the frequency of each word from a input that was a list that was a set of a lot of documents. We did it by defining a map and a reduce. The framework gave us built-in certain operations like splitting, joining, and shuffling that we had to use. And we were clever in the way that we defined really the intermediate values, the intermediate keys and values in such a way that to make use of the shuffle. Okay. So notice that communication happens between, we have several nodes doing this calculation in parallel, but our code didn't really explicitly do communication, right? All we did in our code was define abstractly maps and reduces. The runtime system handled the communication, communication happened in mainly in the shuffle step between the map and reduce. So they did kind of distributed sort of the values based on the intermediate keys and split those up across the nodes, causing the values of the same intermediate keys to go to the same node. There also was a distributed file system in action, this Hadoop distributed file system, that allowed the input, which kind of like abstractly looks like one folder, to actually be distributed across many nodes, and also for the output that's written in parallel by all the reducers to end up in what's abstractly one folder, but actually is distributed across many machines. Okay, so just to repeat some of what I've said, what the Hadoop framework provides is first this Hadoop distributed file system. Secondly, it has this runtime system that does job scheduling and coordination. So it determines how to make use of a cluster of nodes, like which mappers run where, which reducers run where. It also has a scalable distributed sorting algorithm for doing that shuffling step, which is a very important part of the system. It's kind of the most interesting part of the MapReduce process. Okay. Now, you can learn a lot more about this by reading that 2004 Google paper. There's a lot of examples of like how you would implement different algorithms using MapReduce. And if you're interested in this, I encourage you to read that. A few final tips: you can chain multiple mappers and reduces together, so you can do MapReduce, and so on if necessary. And so if you have a complex problem, the way to address it, to figure out how to define it with MapReduce, is to think about what kind of intermediate results you'd want and what kind of communication you want to do, and how to do that by defining intermediary keys that move data, that kind of scatter and gather the data appropriately. Okay. Now, these days, I think Spark is kind of an evolution of Hadoop and MapReduce, and these days I think it's a little bit more popular. And if I were to recommend to someone a single tool for big data analysis, I would probably say Spark, because it actually it gives you map and reduce just like Hadoop does, but it adds to it some additional features. It gives you a little bit more flexibility. It gives you more than just two operators to work with. Like there is still the map and reduce that Hadoop gives you, but there's some other operators. So you don't have to translate everything into a map and reduce. You can use other things that you're more familiar with, like for loops, for example, are available in Spark, and those are parallelized in a simple way. It also has some performance optimizations. In particular, Hadoop tends to use the file system too much. So what Spark does is one of the main things it does is allows intermediate results to be stored in memory. And as a programmer, there's certain things you have to do to use that feature and make it efficient, but it makes it faster. It also makes it a lot easier to run a code that takes many iterations without having to explicitly do like MapReduce over again. You can have like loops that operate more like a regular programming language. Yeah. Okay. Yeah. It also it allows interactive. It has tools for interactive data exploration. Like you just like run code line by line by writing it out, which is pretty cool. The terminology they use is that there's a driver program, which is kind of like the leader program, and that's where you start the code and you start your analysis. Spark also lets you work on regular, like lets you work at a smaller scale as well. You don't have to be using the Hadoop distributed file system. You could write Spark code to run on a single machine, or in like a cloud-based data set that's not using HDFS, for example, a SQL database or some kind of NoSQL database, through the various like data plugins. Like I said before, there are a lot of different, instead of just map and reduce, the Hadoop map and reduce, there also is a one-to-one map, filtering, reducing by key for each loops, and operating on collections. So just like more building blocks to work with that are all implemented in parallel by the runtime system in a cool way. And there are these explicit operations for improving performance, like caching and accumulators, which I don't think we really need to get into too much, but I just know that they're there and understand that one of the reasons people use Spark instead of Hadoop is both because it's easier to program and because it's more efficient, and if you, in the worst case, you can kind of do the same things that are possible in Hadoop with Spark. But Hadoop came first and definitely influenced Spark, and it's still around. People do use it. Yeah. So one of the core innovations in Spark is the Resilient Distributed Dataset, or RDD, which is a way that Spark represents intermediate values as reproducible objects instead of saving to disk. So what Hadoop, this is what makes it more efficient. So you don't have to necessarily save all the intermediate results to disk. Like in between a communication between between the steps, if you're doing a communication, you don't have to save things to disk first before communicating. That saves a lot of time. So like these RDDs are essentially like the big data objects. They can be represented in several ways. They could refer to something that's on disk in the distributed file system. It could be something in memory in your driver program, or it can be a list of code operations based on another RDD, which is interesting. So like instead of storing the code, you can just define, like this bullet point down here shows a sequence of operations that would regenerate the code. I mean the data. So we call that data provenance. So provenance refers to the like origin of something. And in this case, we can if we want to have a record of the data. So if we want to deal with the fact that we want to have robust computation. So even if a node fails, in our big huge cluster, we can still proceed without the whole thing getting lost. We would want to have sort of a backup copy of all the data that's being processed. Hadoop solves this by storing to disk. That's slow, so what instead Spark does is it sometimes just stores a short description of what the steps are needed to recompute a thing. And so if you lose a node, you might take some time to recalculate that what was lost, because what was lost was actually just in memory. So you do have the data in memory. You don't always use this like provenance information to represent the data because you actually need to operate on it. But when it's lost, you regenerate it. If it's lost, you can regenerate it from these steps. Okay. All right, so an example, so it looks a little bit different. It looks more like regular code. So if example here I'm giving is text search, and here are several lines of pseudo Spark code that might do text search. And remember, this is the runtime system will implement this in parallel to run on a lot of machines efficiently. So the first thing we do is define a file. Using Spark, we can open a text file. This path here refers to a Hadoop distributed file system path. This also could be a huge file that's distributed across many machines. And we're going to actually, behind the scenes, process it in parallel, even though our code doesn't explicitly define anything that's really like managing that parallel operation. The next step takes that file and performs a filter operation with this anonymous function here that checks whether the item contains a certain line. So we're looking for all the lines that contain the word error in all capitals. The result here is then mapped to a 1. So for every one of those, for every occurrence, we generate the number 1. And then finally, we reduce those ones with an addition operation that gives us a count. So those things together produce the count of every time the word error appeared in this big file set. And one interesting thing about this is because we're defining everything at a high level, there's a lot of runtime optimization that can happen, especially if we wait to evaluate things. So in particular, this errors value and ones value is not evaluated until we get to the last line, because there's no reason for it to. Until we need it, it's actually better to just wait until we know what we're going to do with the output to figure out where to run it. So in other words, once we get to the final line, only at that point does the runtime system give the instruction to all the nodes to look at their slices of the files, to filter them, to map them to ones, and to reduce those down. Right? If we were to do those individually, depending on what happens later, it might be better to implement them in a different way. Another example here that's much more complex is logistic regression, which is like a kind of machine learning classification, With this problem, we want to find a hyperplane W that best separates two sets of points, and we want to solve it with gradient descent. So on the right-hand side, I have like pseudocode that implements that in Spark. Now, the two new things here in the Spark code is I'm using the cache operator to force something to be stored in memory across multiple iterations for efficiency. And that also means that the next calculation is going to happen on the same machine. And we also use this accumulator operator that allows a kind of like arithmetic addition to happen in parallel efficiently. Oops. So the actual implementation here, I mean, you don't really have, it's okay if you don't really know how logistic regression is implemented, you know, what I mean by this hyperplane separating two sets of points. But anyway, I'll go through it anyway. But you have a set of first you read the set of points, which this Spark operation does from a file. We map it using this parse point is actually a reference to a function. This isn't a variable, it's a function that implements the translation from the text file format to the format here that we're storing. And then we call cache to tell the system that we want that data to stay in memory throughout all the executions of this program. Because in other words, we're going to reuse this. We want to do that efficiently. We initialize a random vector as our starting point for this hyperplane, starting value for the hyperplane. And then we have multiple iterations where we do the gradient descent. So this for loop now is, it's kind of like a new thing. We couldn't do this with MapReduce. We're defining a large number of iterations. Within each one of them, we're defining the gradient with an accumulator. And then for every one of the points, we have this for each operation. This is important because this allows us to define some code that runs in parallel across a lot of nodes. It does this thing here, which is calculate the gradient for the individual points, the update to the gradient for each of the individual points. Sums that up in the accumulator, and then finally at the end we have a gradient that was computed in parallel, and we apply that to the hyperplane that we're trying to optimize, and we repeat until eventually, hopefully, we converge to the best value. Cool. Okay. That was a very quick introduction from a very super simple example to a complex one, but I hope it gives you a flavor of how Spark works. Now, there also is another line of parallel computing in the scientific computing world, which is sometimes called supercomputing or high performance computing. The same basic ideas apply, that you want to have some kind of a framework that gives some structure for how you define parallel analyses and implement some of the common operations that everyone implementing a parallel code would want to use, things like gather and scatter and so forth. So in that world, the tools that's most often used is MPI. OpenMP is another one that's simpler. But this is many decades old, and it works in a different way. It's more of a low-level programming language. You generally have to work in C or Fortran to use MPI. And it doesn't quite as easily work with distributed data sets. It's more designed for a world in which your data is stored in one place on a file server or a file server clustered file system, but then there's a different set of nodes that are doing the calculation, and there's a transfer between those. At the beginning, you do a calculation. So this works well if it's not really a very data intensive application. It's more compute intensive because you do a transfer at first. You run a calculation. You might write outputs in parallel to the disks on the machines, and at the end, you copy that back to the file system. But anyway, it's just a different way of doing. It's just a different and I guess older way of doing distributed computing. But in some senses, it has the same flavor of providing certain primitives like gather and scatter that are useful for lots of parallel computing jobs. And these can work on up to tens of millions of CPU cores. Okay, so to recap today's lecture, I talked about how to efficiently analyze large data set. You need to think carefully about computation and storage. In particular, you want computation and storage to be on the same machine. You want to do the calculation the computation on the same machines where you are doing the storing, where the data is stored, so that you don't have to transfer everything off before calculating and transfer it back. So Hadoop does that by having a Hadoop distributed file system that works along with the Hadoop implementation of MapReduce for implementing distributed calculations. It's a little bit awkward to use because it requires you to express your analysis in a series of maps and reduces and defining intermediate keys and values to make that work. But this is a very influential idea in distributed computing. Spark is kind of like the later evolution of this that provides some of the same functionality, but a lot of new building blocks that make it a little bit more familiar to most programmers. And it also improves performance by storing intermediate results in memory using RDDs, resilient distributed datasets, to allow that to happen, to allow data to be in memory without having to without losing data if a machine crashes. Okay, so it's a little easier for beginners to work with, and also can in many cases lead to better performance. Okay. So just reviewing the whole, I remember this is the last lecture of the class, so just I want to throw up here some things we've talked about, different concepts architecturally across all the different lectures as a review, so you can remember all the things you've learned. So when I started the introduction of this class, I said the goal was for you to learn enough to build your own scalable products, like if you're doing your own startup or you're joining a company where they're building something new, and to have you actually be able to contribute to that like architectural level design and not just have to follow others' advice. Sorry, this should be a U. But to actually like know how to build it yourself, and to look at a big system. If you go to a big company, to understand why they have the different components they do, and more than just like knowing how to implement the syntax of a programming language. Like writing code is one thing, building a system is another. Okay, so I hope that this class has helped to fill you in on some of that. If you want to explore these topics more in a university setting, then these are some classes I'd recommend. I think I've mentioned these already. So distributed systems is the most closely related, more like theoretical approach to some of these same topics. Computer networking is very relevant. Operating systems also relevant, and intro to databases would be another closely related class. All right. Thanks for joining. See you later, and good luck. Happy building.